Hey, Sammy. And so that's kind of how we want to think about function. Where does the function of things come from? We're looking at it now. So stem cells are osteochondral progenitor cells. It is from the embryonic mesenchyme that osteoclasts come from in the beginning of time. So stem cells in bone world, stem cell undifferentiated can go off and become an osteoblast, an osteoclast, an osteocyte. But once differentiated, has to go off and become its own individual cell. Woven bone, collagen fibers randomly orientated. If a bone is broken or a bone is just developing, it is woven. But otherwise, no. So mature bone, so bone that isn't just developing, it's mature, it's lamellar. It's an osteon process, a canal with evenly distributed layers around it, lamellar layers, right? So that's what a lamellar layer is. It's lamellar bone is layers evenly distributed. And anytime you see the word lamellar, it means that there's evenly distributed layering around something. One layer, another layer, another layer. Lamellar. And so, cancellous bone, that's trabeculi. Remember that cancellous bone is still made with osteon processes. It just grows out of the compact bone in the medullary cavity towards the center of the medulla at every epiphysis. And this gives the bone greater strength and keeps it light, right? So compact bone, of course, dense arrangements of osteon processes. So the bone matrix, this is a great example of why we need both. So here we have a bone with just calcium phosphate and no protein. And here we have a bone that's got a lot of protein with very little calcium. So this bone can tie itself in a knot, and this one shatters. And the story I always tell at this point in time is a true story of a former Kung Fu student of mine. His name was Aaron. And he was a good Kung Fu student, but even a better young man. He decided he was going to go to Kenya and volunteer and build schools. So he went there 3 times in total, got malaria the first time, went back twice more, spent 6 years in total there, 2 years each time. Committed to helping other people in the world. But his first day arriving in Nairobi, he was went there for 5-10 minutes, and he felt some bump into him, and he checked for his wallet. Sure enough, his wallet was gone. So off went a young man running down the street. Aaron was a fit, kind of go-getter guy, and so he chased him down. We caught up to him. He reached out and grabbed him by the arm. When he grabbed him by the arm, it broke in his hand. His wrist shattered in his hand. He was devastated. Couldn't believe that the guy's arm broke. He just grabbed it and it broke. So he got his money back, but as it turns out, he felt devastated that he had hurt this young man so bad. So he wanted to take him to the hospital and deal with it. In the end, he ended up meeting the family and everything else. He found out that he was extremely poor and had been starving. His family was starving, and they had no protein in their diet, or so little protein that his bones had become brittle, just like this, right? So they had become so brittle because of a lack of protein that they would shatter in the hands of this rather strong young man. So ultimately, when we contemplate nutrition, and we live in a world that's full of nutrition, it's very wealthy, we can eat what we want. Certain places of the world where a lack of protein can cause brittleness and the breaking of bones. We're just walking will cause your bones to break. So we are fortunate and do eat protein. If you're a vegan, you can get protein in the vegan world, no problem. I was one for a while. But remember to eat your B12, supplement B12. So moving on, an osteoblast, of course, builds formation of bone, ossification or osteogenesis. So familiarize yourself, if you will, with these 2 words, ossification and osteogenesis. Osteo, bone, genesis, to make, right? So to make bone, pretty straightforward words. So ossification or osteogenesis is the process. Yes?
Sorry, are those 2 words synonymous?
Synonymous, yeah. Synonymous, one with the other. You can use either one. That's no problem. So collagen is produced by endoplasmic reticulum. Remember, rough endoplasmic reticulum produces proteins. One of the jobs of an osteocyte would be to produce the proteins to maintain the matrix. An osteocyte maintains the matrix. What is it doing then? It's producing the protein that's required to maintain the matrix. It's producing collagen fibers, but it's also releasing calcium and phosphate when that's required to maintain the ground substance. So it maintains the ground substance, calcium phosphate, and it maintains the proteins by producing them via its nucleus. So the nucleus has, via DNA, the appropriate recipes for producing the collagen fibers for bone. So an osteocyte, it creates interstitial growth. What's the job of an osteocyte? Interstitial growth. What's the function of an osteocyte? Interstitial growth, meaning I should see pens just applying. Interstitial growth, meaning that growth between cells, right? Between each cell. So looking at our diagram up here, that's a cell, that's a cell. The job of that cell is to keep the matrix around it healthy. The job of this cell is to keep the matrix around it healthy. So interstitial growth, growth between cells, right?
What cell does that? Osteoblast or osteocyte?
Osteocytes.
Okay.
An osteoblast creates appositional growth, right? So what is the function of an osteoblast? Appositional growth. It builds the bone on the outside, right? It lays down the layer. Let's go ahead just a little bit at this point. I'm going to show you a picture that's a little later on, but it's a valuable picture. Play it. This one. This is appositional growth. What we see here is that the bone is being eaten away on the inside by osteoclasts. So the bone has to grow on the outside. An artery and a vein lie up against the periosteum. The periosteum wraps around the artery and vein, keeps wrapping it around until it creates an osteon process. So that's appositional growth. The addition of one osteon process and another osteon process creates appositional growth. And osteoblasts give us appositional growth. An osteocyte gets embedded into the bone, correct? It's embedded in the bone. It's embedded in the matrix. So the job of the site is to produce ground substance and proteins. And the ground substance and protein are produced by the cell, and that's interstitial growth. So when we think of the function then of osteocytes and osteoblasts functions to create appositional growth, osteocytes function for interstitial growth. Yes? Yes, yeah, exactly. We need so much more energy and oxygen for that production, energy production, for all the proteins we're producing. That's exactly what it is. So what? Yes, always. Yeah, every time. Yeah, much more faster than you think. Bone, of course, without oxygen, you can't run mitochondria, right? So the more oxygen you bring to mitochondria, the more ATP it produces, the more ATP it produces, the more energetically it can move materials across its membrane and create proteins, etc. Right? So when we look at this idea then of osteoblasts and osteoclasts, or osteoblasts and osteocytes, then that's what we're really talking about. Where am I now? Okay, ossification. Now, so the osteocyte lives within a lacunae. We talked about that. That's a space, right? So it lives within a space. It's interstitial growth. Nutrients diffuse through tiny amount of liquid surrounding the cell and filling the lacunae and canaliculi. So remember, the canaliculi are these little canals, right, that go between the lacunae. So lacunae are the homes. So what is the function of a lacunae? To house a cell. What is the function of canaliculi? It is a little canal that brings nutrient and other ions for communication to and from one osteocyte to the next.
Are osteoblasts and lacunae as well?
They eventually become an osteocyte. Once they've created a lacunae and they're embedded in the lacunae, now they're an osteocyte. They're not an osteoblast anymore. So an osteoclast, of course, coming from stem cells, they derive from mesenchymal osteochondral progenitor cells. Ah, that's a wonderful thing to say. Osteochondral progenitor cells. This stuff, you just can't make this stuff up, can you? Right? Embryonic mesenchymal osteochondral progenitor cells. That's what you would say here. And so this morning I'm in the library. I mean, not the library. I was at the library, but I went to the bank, and the woman said, "So what are you doing this afternoon?" And I said, "I'm giving a lecture on bones." And she said, and the teller said, "See if you can explain how they were able to increase the bone marrow in my tooth." So I said, "By the introduction of osteochondral progenitor cells." And she said, "Ah!" So I was talking about this to a teller at the bank today. Embryonic mesenchymal osteochondral progenitor cells. They become chondroblasts or osteoblasts, right? So it's from this stem cells that we get the osteochondral, but they're released via the visceral layer of the endosteum. So endosteum is releasing these cells. So when we look at osteoblast, reabsorption of bone, where cell membrane borders bone, reabsorption takes place, hydrogen ions or acid is pumped across the membrane and eats away the bone. So the endosteum is literally pumping acid onto the bone. And then there's a release of enzymes that digest the bone. And these are derived from monocytes, which are formed from stem cells. So there are, if you think about it in a really intense way, there are about 6 different cell or things that contribute to the development of an osteoclast. So from our perspective, from this class perspective, if you have to answer any kind of question related to where does an osteoclast come from, where is it derived from, it's ultimately derived from mesenchymal progenitor cells, but it's released by the endosteum. So that's as much and as in depth as you need to go with osteoclast. And reabsorption of bone is as good as you need to say. What's its function? Reabsorption of bone would be good enough. When I talk about woven, formed during fetal development and fracture, yes?
Just about your osteoclasts, you mentioned earlier that they become osteocytes.
No, osteoblasts become osteocytes.
Oh.
No, osteoclasts do not.
And you said derived from mesenchyme monocytes. Derived from monocytes?
Yeah, monocytes are a type of white blood cell that's produced in bone marrow. And ultimately, I just wanted to go back on this. Keep it simple for you. Keep it stem cells in your mind. Stem cells and endosteum. Keep it simple, right? Osteoclasts come from stem cells, and they're released by endosteum. Nice and simple. Now, fetal development. When a bone just develops, it's woven. When a bone breaks, it weaves. But then it remodels, removing old bone and adding new. Woven bone is remodeled into lamellar bone. So when it's remodeled, it becomes lamellar. It looks like instead of random, it becomes groups of osteon processes like you saw on the slide. One and another, each nicely distributed. That is considered remodeled or lamellar bone. So mature bone in sheets called lamellae, fibers are oriented in one direction in each layer, but in different directions in different layers of strength. So one layer of osteon process has its fibers running one way. The next layer will have the fibers the other way. Let's look at this idea. Who here has heard of plywood? Raise your hand. All right. You never heard of plywood before? No? Plywood is what you put on.
She's supposed to spit water.
So plywood The reason plywood is a success is you take really thin layers of wood and you lay them so the fibers of one lie this way, and then the next one, the fibers lie the opposite way. If you take and lie all the fibers of, say, a paper-thin sheet, and all the fibers are the same way, and you put, say, 20 of those pieces of paper together, and you lay a weight 5 pounds on it, it will go right through the paper. If you take 10 of those sheets and alter them so that the fibers cross each way, then you can lay the 5-pound weight on with half as many sheets, and it will hold it. Cross-fibering strengthens things. They get stronger, right? So we cross-fiber in lamellar bone. We lay fibers down opposite to one another to increase strength. Yes, no. Yeah, chipboard where it's just kind of laying everywhere. Exactly. Fibers are laying like dense, irregular connective tissue, right? And eventually they're all brought into alignment and evenly displaced, one facing one way, one the other. And this brings great strength. So lamellar bone has great strength because it lays down layer after layer, and each layer, the fibers are in the same direction but opposite to the layer before it, right?
Like Jenga?
Pardon me?
Like Jenga?
Like Jenga, yeah, yeah, exactly. Yeah.
Okay.
Good one. I'd like to bring it to the real world. Cancellous bone then. I'm going to tell you something about trabeculae here. There's some functions that are really quite interesting. So we see that trabeculae, interconnecting rods or plates of bone like scaffolding, growing out from the compact bone towards the center. And it happens around in an epiphysis, right? In the medullary cavity of the epiphysis. That's where it occurs. So space is filled with marrow covered with endosteum. So this whole area is covered with endosteum. One of the things we find with osteoporosis, especially as women age, they get it a lot more than men, a reduction in calcium. Reduction in calcium means that the body goes to the bones to get the calcium.